Have you ever, like, tried to make a decision with the group of friends and everyone wants something different?
Yeah, all the time.
Like maybe choosing a movie to watch or
Yeah.
even something simple, like what to order for dinner. You got everyone's different preferences, and they're not really comparable, are they? Like, how do you weigh your friend's craving for pizza against your love of sushi?
Yeah, exactly. It's this everyday challenge, turning individual likes and dislikes into some kind of group agreement. It's harder than it seems.
And that's actually exactly what we're getting into today with social choice theory.
Hmm.
How do you take these individual opinions and turn them into something?
Hmm.
Well, something fair for the whole group.
That's the crux of it. Social choice theory, we often call it SCT for short.
Oh,
SCT.
SCT.
It looks at those situations where you're trying to make a choice as a group, but you can't just measure everyone's happiness or preferences on some kind of universal scale and just add it all up. It's not that easy.
Nope.
So, social choice theory dives headfirst into this problem. How do you get from those individual rankings to a fair and logical outcome for the group? Especially when you're dealing with things like personal well being, which, let's be honest, can be ranked, but it's pretty hard to assign a number to, right?
Right. You can't really measure happiness on a scale of 1 to 10 in any objective way.
Exactly. But this is actually a really important problem because it helps us understand how a lot of real world decision making systems work. Think about everything from your local elections to the way governments make huge policy decisions.
And that's our focus for today. We're going to unpack those core ideas, look at the challenges, and try and understand how to make fair decisions as a group. And we'll even use a real example, like let's say you have three friends, Ann, Bob, and Shu. They're trying to decide between three policies, policy 1, 2, and 3. Ann ranks them, policy 1, then 2, then 3. Bob goes for 2, then 1, then 3. And Shu prefers 3 first, then 1, then 2. So how do we take those different preferences and turn them into one list that reflects what the group as a whole wants?
It's like deciding on what takeout to order, right?
Yeah.
Maybe it's whoever shouts tie first, or maybe there's a whole voting system.
That's where the idea of a social welfare function comes in, right?
Precisely, a social welfare function.
Or SWF.
Yeah, or SWF for short. It's basically a rule.
Okay.
And this rule takes in everyone's rankings. We call this set of rankings a preference profile.
The preference profile.
Right. And then from that preference profile, it spits out a complete ranking of all the choices, from best to worst, even allowing for ties if some are equally good.
So, like with our takeout example, the social welfare function is the thing that takes everyone's individual desire for, say, burgers, pizza, or Thai food, and it crunches those preferences to figure out what the whole group should order.
Exactly. And today we're going to look at some of the big ideas in social choice theory, different methods it uses, and even some of the surprising limitations that come up. But hey, before we go too deep, if you want to really get a handle on all this, you can always check out gradeguru.nl for super detailed summaries and practice tests.
Always good to have those extra resources.
For sure.
All right, so let's dive in. What's like the fundamental problem that social choice theory is trying to crack? What's the big challenge here?
Well, at its heart, SCT is trying to solve this. How do you take all those individual preferences that people have, those ranked lists of what they like best, and blend them together? The goal is to either get a single, social ranking that reflects the whole group's preference, or just pick the best option for the group, or maybe a few equally good options if there's a tie.
So it's like we're taking everyone's personal opinions and trying to create some sort of like group consensus.
Yeah, exactly.
Okay, so how do we actually, do that? How do we go from those individual rankings to a group decision?
That's where those social choice functions and social welfare functions we talked about earlier come in. A social choice function, or SCF,
The CF.
takes a preference profile, which is the collection of everyone's rank lists, and then it picks out a winner or winners. It just gives you the best option or
Yeah.
options. Now, a social welfare function, an SWF, is a bit more nuanced. Instead of just picking a winner, it creates a full ranking of every option from best to worst, and it even allows for ties if some options are equally preferred.
Right.
And actually, there's a cool connection between the two. You can get an SCF from an SWF. Basically, you take that full ranking from the SWF, and the top ranked choice, or choices, automatically become your winners according to the SCF.
Gotcha. So SWF gives you the whole ranking, and SCF just picks the winner.
Yeah.
Okay, let's dig into those social choice functions. You mentioned 4 specific ones earlier.
Yeah.
Let's start with the plurality rule. I feel like I've heard of that one before.
It's probably the most straightforward one and the one
Yeah.
people use the most. With the plurality rule, the winner is just whichever option gets the most first place votes. Simple as that.
So like going back to that takeout example, if 2 friends say tie is their favorite, 2 friends say pizza and 3 say burgers. Then burgers would be the plurality winner, just because it has the most people who ranked it first.
Exactly. 3 people put burgers at the top of their list more than any other option, so burgers win.
That does seem simple, but you asked earlier, is this always the best way to do it? What makes you question the plurality rule?
Well, the thing is, plurality only looks at the very top preference. It completely ignores how people rank all the other options. Let's think about those burgers again. Even though they got the most first-place votes, what if they're everyone else's absolute last choice? Like, maybe those who voted for Thai or pizza really, really don't want burgers.
Okay, I see what you mean. So just looking at first-place votes might not capture the whole picture. Like maybe there's another option that more people would be happy with, even if it wasn't everyone's top pick.
Exactly. If we compared all the options head-to-head, like in a tournament, we might get a different result. Remember, 2 people put Thai first, 2 put pizza first, and 3 put burgers first. But if we just compare burgers and pizza head-to-head, well, the 2 who ranked Thai first, they both put pizza second and burgers last. And obviously, the 2 pizza lovers prefer pizza to burgers. And even among the burger fans, they all actually have pizza as their second choice.
So that's 4 votes for pizza and only 3 for burgers, even though burgers had more first-place votes overall.
Precisely. And if you do the same thing with burgers and Thai, the Thai lovers, of course, prefer Thai. The pizza lovers have Thai last. And again, all 3 burger fans actually have Thai last on their list, too.
So again, Thai beats burgers 4-3.
Exactly. So even though burgers won in the plurality rule, it looks like more people would actually prefer either pizza or Thai if they had to choose between just those 2.
So it's about more than just who gets the most top votes. It's about, understanding the overall preferences of the group, which leads us to that second method you talked about, the Condorcet method.
Yes, the Condorcet method. This method is all about those head-to-head comparisons. We're looking for a Condorcet winner. That's an option that beats every other option in a head-to-head vote.
Like a champion.
Exactly. And on the flip side, a Condorcet loser is an option that loses to every other option in those head-to-head matches.
Like in our takeout example, pizza is the Condorcet winner.
Exactly. We already saw it beat burgers. And if we compare pizza and Thai, the Thai fans have pizza second. The pizza lovers, well, they pick pizza. And the burger fans also have pizza second and Thai last.
So pizza wins again, 5-2. Pizza beats both burgers and Thai, so it's the Condorcet winner. And burgers, losing to both, is the Condorcet loser.
Precisely. This Condorcet winner is like a really strong contender for the best choice, because it has the support of the majority against every other option.
Makes sense.
But there's a catch. A Condorcet winner doesn't always exist.
Oh.
Yeah, think about this. Anne says Thai, then burgers, then pizza. Bob says burgers, then pizza, then Thai. And Chu says pizza, then Thai, then burgers.
Okay, so everyone has a different favorite.
Now let's do those head-to-head comparisons again. Thai loses to pizza because Bob and Chu prefer pizza. Burgers lose to Thai because Anne and Chu prefer Thai. And pizza loses to burgers because Anne and Bob prefer burgers.
So everyone's favorite loses to someone else's favorite.
Exactly. It's a cycle, right?
Like rock, paper, scissors.
Yeah. No single option wins against all the others. So in those cases, the just pick the Condorcet winner rule, well, it doesn't work.
Because there isn't one.
Yeah.
Okay, so what do we do then? What's the next social choice function on our list?
It's the Copeland rule.
Copeland rule.
And
okay.
this one tries to capture the spirit of that Condorcet winner, even when one doesn't actually exist. So what you do is you look at each of those head-to-head matchups. The winner of each matchup gets 1 point, the loser gets 0, and if it's a tie, they each get half a point. You add up all the points and the option with the most points. That's the Copeland winner.
So even if there's no single champion, this method still tries to find the option that does best in those individual matchups.
Yeah, exactly. And the cool thing is, if a Condorcet winner does exist, it will always win with the Copeland rule, too, because it would have won all its matches and gotten the most points.
Makes sense. Yeah, you mentioned something about an exercise for this one.
Right. Exercise A in our materials dives into this. It asks you to look at a specific set of preferences, a preference profile, and figure out 2 things. First, is there a Condorcet winner in that set of preferences? And second, if there isn't, does the Copeland rule give us a clear winner? This exercise shows you how the Copeland rule can still find a winner even when there's no clear Condorcet champion.
Okay, so we've got plurality, Condorcet, and Copeland. What about that 4th SCF, the border rule, right?
Yes, the border rule. This one's interesting because it actually looks at the whole ranking, not just the first choice or those head-to-head battles. Imagine you have, like, 5 options. With the border rule, you give points based on where each option falls in someone's ranking.
So the higher up an option is, the more points it gets.
Exactly. In this example, with 5 options, the top choice gets 4 points, the second choice gets 3, all the way down to the last choice, which gets 0. Add up all the points from everyone's rankings, and the option with the most points wins.
Let's try that with our takeout example. The Thai, pizza, burgers won.
Sounds good.
We have 3 options. So first place would get 2 points, second place 1 point, and last place 0 points.
Right.
Okay, so Thai got 2 first place votes, 2 second place votes, and 3 last place votes. That's 4 points for the first place votes, 2 for the second place votes, and 0 for the last. So Thai gets a total of 6 points.
Okay, and burgers.
Burgers got 3 first place votes, which is 6 points, and 4 last place votes, which is 0 points. So burgers also get 6 points.
Interesting. It's a tie so far. And pizza.
Pizza got 2 first place votes, which is 4 points, plus 5 second place votes, which is 5 points. So pizza gets 9 points.
So, using the border rule, pizza wins this time. Fascinating.
Yeah, this is really interesting because earlier, burgers won with the plurality rule and pizza won with the Condorcet method. Now, pizza is also the border winner. It really shows how using a different rule can change the outcome.
And that's actually what Exercise B is all about. It asks you to find the border winner for that same preference profile we looked at earlier with the Copeland rule. It's another example of how those different SEFs can lead to different results, even with the exact same preferences.
Right, and you even mentioned another example, right, where B was the border winner, D won with plurality, and C was both the Condorcet and the Copeland winner.
Precisely. It really highlights that the method you choose can significantly change what's considered the best outcome. And you mentioned one more method, instant runoff voting.
Right. Instant runoff voting, or IRV.
Uh,
This one is kind of interesting. It's actually used in some real-world elections. Basically, you start by seeing if any option has more than half the first place votes, a majority.
Okay.
If so, that's the winner. Simple. If not, you get rid of the option with the fewest first place votes. Then you look at all the ballots where that eliminated option was the top choice, and you move those votes to the voter's second choice option.
So you're redistributing the votes from the least popular option.
Exactly. And you keep doing that, eliminating and redistributing, until one option has a majority of the votes.
Can you walk us through an example?
Sure. Let's use that preference profile, Profile P that we mentioned before.
With A, B, C, and D.
Yeah. 7 people have A, B, C, D. 7 more have C, B, A, D. 8 have D, C, B, A. And 5 have B, A, C, D. So in the first round, no one has a majority. There are 27 votes total, and no option gets more than half. Option B only has 5 first place votes, the fewest. So we get rid of B.
Okay, so what happens to those 5 votes?
We look at the ballots where B was the top choice, and we see that all those people had A as their second choice. So those 5 votes go to A. Now A has 12 votes. Its original 7 plus the 5 from B. Option C still has 7 and B still has 8. Still no majority.
Right.
So now C has the fewest votes with 7, so we get rid of C. We look at the ballots where C was first and their second choice is B, but B is already out.
Ah, okay.
So we go to their third choice, which is A. So A gets those 7 votes too. Now A has 19 votes and it still has 8. A has a majority, so it wins.
It's kind of like an elimination tournament for choices, right?
Yeah.
You mentioned something about a clause 2 in the definition of IRV.
Yeah, sometimes when you're eliminating the options with the fewest votes, you might have a tie, and you end up eliminating more than one option at the same time. Clause 2 says that in that case, all the options that are left are considered winners.
So it's like a multi-way tie.
Exactly. Exercise C in our materials shows why that clause is important. But getting back to our example, A1 with IRV. But earlier, B1 with Borda, C1 with Copeland, and Ed1 with plurality, all with the same set of preferences.
It really shows how the method you use for making the decision has a huge impact on who or what wins. So how do we choose the right method?
That's a great question. With so many different ways to do this, how do we figure out which method is like better or fairer?
That's where the concept of these, we call them axioms, comes into play.
I'd say.
It's basically a fancy word for like desirable properties.
Yeah.
We use these axioms to judge the different social choice functions. We try to figure out which SCF satisfies these properties that we think are important for a fair and reasonable system. Ideally, what we'd love to find is a set of axioms that only one SCF satisfies. That would give us a really strong reason to choose that particular method because it would be the only one that ticks all the boxes.
So like a set of criteria that helps us pick the best, fairest voting system.
Exactly. So let's talk about some of the key axioms. We'll start with anonymity.
Anonymity.
Yeah, anonymity means that it shouldn't matter who has which preference.
What do you mean?
Okay, so let's say we have three people, Fred, Bart, and Tim. Fred says New Zealand is his favorite place, Bart says Korea, and Tim says Belgium. Now, if we swap Fred and Bart's preferences, so now Bart likes New Zealand and Fred likes Korea, the outcome of the vote should stay the same.
It's like saying the votes are what matters, not the voters themselves.
Exactly. The identity of the voter shouldn't change the result, only their preference. And that's what anonymity is all about. And it turns out that plurality, Copeland, Borda, and IRV, they all satisfy anonymity. But imagine a system where there's one specific person, a dictator, and whatever they say is the winner. That wouldn't be anonymous because if someone else had the dictator's preferences, the outcome might change.
Right.
So anonymity is one important criterion. What's next?
You mentioned neutrality earlier.
Neutrality. This one's about treating all the choices fairly.
How so?
Okay, let's say Korea wins an election. Now imagine we just swap the names of Korea and Belgium everywhere in everyone's preferences. If the voting system is neutral, now Belgium should win.
So it's not biased toward a particular option.
Exactly. And again, plurality, Copeland, Borda, and IRV. They all satisfy neutrality.
Okay.
Now there's an exercise D, that asks you to look at a specific rule. It's called the two-thirds majority or status quo rule.
Two-thirds majority or status quo.
Right. And this exercise shows you how that rule actually violates neutrality. That's a hint that even some rules that seem reasonable can have hidden biases.
Interesting. So anonymity is about treating all voters equally, and neutrality is about treating all the choices equally. Makes sense. And you said there's a connection between these two axioms and some bigger ideas.
Yeah. Anonymity and neutrality. Together, they're like the embodiment of the principle of equal treatment of equals. It means that everyone's preferences are counted the same and all the choices are treated fairly. And neutrality in particular, that's really tied to the idea of popular sovereignty. It's the idea that the people's will should determine the outcome, not some built-in bias in the system that favors a specific option.
So it's about democracy, really, making sure everyone has an equal voice and the system itself isn't tipping the scales. What's the third axiom on our list?
That would be positive responsiveness. This one is about how the outcome should change when someone increases their support for an already winning option.
Okay.
Positive responsiveness says that if someone changes their preferences to favor an option that's already winning, and they don't change anything else in their ranking, that option should become the only winner.
So like if a candidate is winning an election and then they get even more support, they should definitely still win, right?
In a system that satisfies positive responsiveness, yes.
Can you give me an example?
Okay, let's go back to Fred, Bart, and Tim. Remember, they were choosing their favorite places.
Right.
So Tim initially says Belgium, then Korea, then New Zealand. Now imagine he changes his ranking to Belgium, then New Zealand, then Korea. He's just moved New Zealand up, right?
Right.
Now, if New Zealand was already a winner before this change, then after the change, it should be the only winner.
Makes sense.
There's an exercise E, that shows how instant runoff voting, that system we talked about earlier, actually violates positive responsiveness.
Oh, really?
Yeah. Imagine this. A candidate is winning and then gets a bunch more support from people who originally were voting for someone else. But because those new supporters initially voted for someone who still had a tiny number of votes, the original winning candidate might actually lose, because when that other candidate is eliminated, their votes go to someone else.
That seems counterintuitive.
Yeah.
The candidate got more support and lost.
Yeah. Exactly. And it happens because IRV doesn't always respond in a predictable way to changes in support. Exercise F shows that the plurality rule also violates positive responsiveness.
So even those seemingly simple and common systems might not always behave the way we expect when it comes to fairness and representing the will of the people. So where do we go from here? Does any voting system satisfy these axioms?
There is some good news. There's a theorem called May's theorem that looks at the specific case where there are only two options to choose from, like a yes or no vote or choosing between two candidates.
Okay.
And May's theorem says that in those situations, with only two options, majority rule is the only social choice function that satisfies anonymity, neutrality, and positive responsiveness.
That's pretty significant. Does that mean majority rule is the best system when there are only two choices?
May's theorem definitely gives us a strong argument for using majority rule in those cases, and it actually has a prominent place in both formal social choice theory and in democratic theory as an argument for democratic rule when you're faced with a binary decision.
That makes sense. But most real-world decisions Involve more than just two options.
Right. And that's where things get really interesting, and we bump into one of the most famous and maybe even a little unsettling results in all of social choice theory, Arrow's impossibility theorem.
Arrow's impossibility theorem.
Yeah, and to get into that, we need to shift gears a bit and go back to those social welfare functions. Those, remember, give us a complete ranked list of all the options.
Right. Instead of just picking a winner, it gives us a social ranking of everything.
Exactly.
And you gave us some examples of those earlier, like the plurality SWF and the Borda SWF.
Yes, the plurality SWF uses the number of first-place votes to create a ranked list. The Borda SWF uses the total Borda points. And even something simple, like if we just said whatever Fred's preference is, that's the social ranking, that would technically be a social welfare function. We could call it like Fred's dictatorship, SWF.
Okay, so there are a lot of ways to get to a ranked list.
Yeah.
But you said Arrow's theorem has to do with using pairwise majority rule to create that list.
That was a natural place to start. You could imagine a system where society prefers option X over option Y if the majority of people prefer X to Y. Simple. Right.
Seems reasonable.
But here's the problem. Those majority preferences, they can be intransitive, meaning that even if the majority prefers X over Y and Y over Z, it doesn't automatically mean that the majority prefers X over Z.
Huh?
Yeah. It's called the Condorcet paradox, and it was first pointed out by Nicolas de Condorcet way back in 1785. Remember our friends Anne, Bob, and Chu choosing between Thai, burgers, and pizza. Anne prefers TBP, Bob prefers BPT, and Chu prefers PTB. Now, if you look at the majority preferences, Anne and Chu prefer Thai over burgers, so the majority prefers Thai over burgers.
Okay.
Anne and Bob prefer burgers over pizza, so the majority prefers burgers over pizza. But Bob and Chu prefer pizza over Thai, so the majority prefers pizza over Thai.
So Thai beats burgers, burgers beats pizza, but pizza beats Thai.
Exactly. It creates a cycle, right?
It does.
It means that trying to create a social ranking using pairwise majority rule, well, it doesn't always work because you can end up with these contradictions. It doesn't always define a proper social welfare function.
Right.
And those preference profiles where we get this cyclical majority preference, those are called Condorcet profiles.
Condorcet profiles. Okay, so pairwise majority rule has some problems.
Right. And to tackle those problems, Arrow came up with 3 criteria that he thought a good social welfare function should meet. He called them axioms. The first is the weak Pareto principle.
Weak Pareto principle.
Yeah. It basically says that if literally everyone in the group prefers option X to option Y, then the social ranking should also prefer X to Y. It seems pretty obvious, right? Like if everyone agrees on something, the group's ranking should reflect that.
It does seem pretty fundamental.
Yeah.
Okay, so that's weak Pareto. What's the second axiom?
The second is no dictatorship. This one's pretty straightforward.
No dictatorship.
It just means there shouldn't be any single person whose preferences always determine the social preference. Like no matter what everyone else thinks, Fred's preference wins.
Okay, that definitely seems like a core principle for any kind of democratic system. You can't just let one person call all the shots.
Exactly.
Okay, what's the third axiom?
The third one is called independence of irrelevant alternatives. It's often shortened to IIA.
IA.
This one's a little more tricky.
Okay.
It says that the social preference between two options, let's call them X and Y, should only depend on how individuals rank X and Y.
Go.
It shouldn't be influenced by how people rank some other irrelevant option.
Can you give me an example of what you mean by that?
Sure. Let's imagine Anne and Bob are choosing between a banana, an apple, and a cherry.
Classic choices.
Right. So in one scenario, Anne ranks them banana, then apple, then cherry. Bob ranks them cherry, then banana, then apple. And let's say our social welfare function says that society prefers banana over cherry. Now imagine that Anne and Bob's preferences for banana and cherry stay the same, but their preferences regarding apple change. Now Anne ranks them apple, then banana, then cherry. And Bob ranks them apple, then cherry, then banana. So their rankings of apple have changed, but their rankings of banana and cherry relative to each other are still the same.
Right.
IIA says that the social preference between banana and cherry shouldn't change because the individual preferences between just those two haven't changed.
I see. So if the group preferred banana over cherry before, they should still prefer it now, even though their views on apple have changed.
Exactly. Exercise H gives you another scenario where you can really explore the implications of IIA.
Okay, so we have the 3 axioms: weak Pareto, no dictatorship, and IIA. They seem pretty reasonable. So, like, what's the big problem? What did Arrow prove that's so impossible?
Well, Ayres' impossibility theorem says that when you have three or more options to choose from, there's no social welfare function that can satisfy all three of those axioms at the same time.
Wait, seriously. So you're saying that no matter how hard we try, no matter how clever we are, we can't design a voting system that's fair according to all three of those axioms.
That's exactly what Arrow's theorem tells us. If we want a system that doesn't have a dictator and respects everyone's preferences when they all agree, weak Pareto, we have to give up IAA, that independence of irrelevant alternatives. Or if we really want IAA, we have to give up one of the other two. There's no way to have it all.
That's kind of mind-blowing.
It is, right. And what makes it even more significant is that most people agree that weak Pareto and no dictatorship are like the bare minimum for a democratic system.
Yeah.
And while people debate about IAA, a lot of people think it's pretty crucial too.
So this theorem really throws a wrench into things, doesn't it? It suggests that finding a truly fair and representative voting system is a lot harder than it seems. You mentioned earlier that social choice theory is about more than just voting. Can you expand on that a bit?
Yeah, absolutely. We've talked a lot about voting and how to combine people's preferences, but in a broader sense, social choice theory is about any situation where you have a bunch of rankings based on different criteria, and you're trying to combine those rankings into one overall ranking, or pick a single winner.
Okay.
Think about like trying to figure out who's the best athlete in track and field. You have rankings in running, long jump, weightlifting, all these different events. How do you combine those to say who's the overall champion?
Right. Or even something like the presidential elections. You have all these voters with their own preferences, and you need to figure out who wins.
Exactly. So it's really any situation where you have multiple inputs that provide rankings, and you need a system to turn those into a single output, either a final ranking or one winner.
Okay, so it's not just about individual preferences.
Okay.
It could be rankings based on any criteria, really.
Right. And those criteria could be anything, really. It could be
Yeah.
votes, preferences, judgments, even something like measures of well-being, as Christian List puts it. Social choice theory is about studying procedures and mechanisms for collective decision-making.
Collective decision-making.
Yeah. It's about looking at how we take individual inputs, those rankings based on whatever criteria we're using, and turn them into collective outputs like decisions, preferences, judgments, or overall rankings. And in this very broad sense, everything we've talked about today, all this stuff about going from individual preferences to a group decision, all falls under the umbrella of social choice theory.
So it's a really broad field.
It is. And some of the big questions it looks at are, how do groups pick winners? What are the properties of different voting systems? What makes a system democratic? How can groups form coherent preferences? And how can we rank different options in terms of social welfare? Big questions, right?
Huge questions. So before we wrap up, can you give us like a quick recap of what we covered, just the main takeaways for anyone who's trying to get their head around this stuff?
Yeah, for sure. So we started with this challenge of figuring out how to combine individual preferences when you can't directly measure those preferences, just rank them. That led us to social choice theory. We talked about preference profiles, which are just collections of all those rankings. And then we looked at a bunch of different social choice functions like plurality rule, Condorcet method, Copeland rule, border rule, and instant runoff voting.
Right.
We saw how those different methods could actually lead to different winners even.